Well, we should go ahead and get started. Happy Wednesday. We are so close to being done here. Um, we need to just kind of do a little bit more of covering of our basics of cache architecture, and then we can cover more of the analysis of the performance of those of cache. And that's pretty much it for this semester. We'll see each other 3 or 4 more times, and that's pretty much it this semester. So let's make the most. Let's make the most of the time that we have available together here. So where we left off on Monday was just this in-class exercise where we were trying to figure out for this relatively simple cache structures here, a 4 entry cache and an 8 entry cache, which access pattern would lead to hits and misses for each of the caches. And we got most of the way through it on Monday. A couple takeaways. One is that locality is important, obviously, and that's what this cache is attempting to take advantage of. But there's a little bit of luck potentially involved, certainly for direct map caches. We have multiple different addresses that all map to the same directly mapped location in your direct mapped cache. And whether or not there's going to be the values you expect in the cache or not really does depend on the order in which those accesses happen. So what we had in this example here was we were trying to fetch from address 0 followed by eventually address 4. And in theory, and then 0 again. In theory, that's a good access pattern for us, right? Because in theory, we're accessing 0 and then we're accessing 0 again. That is temporal locality, right? That meets our definition of temporal locality. But it just so happens that in this 4 entry cache, where we take the least significant bits as needed to form the index and use the remainder of the bits to form those tags, that kind of metadata storage in the cache, because of the order in which those accesses happen, where we had a 0 followed by a 4 followed by a 0, and then followed by a 4 again. Those were all going to be misses in this smaller cache because 0 and 4 map to the same exact location, and consequently, the data that you wanted wouldn't be there at the time that you needed it. You need to have subsequent, consecutive accesses to a location for there to be a cache hit. So if you're asked to analyze that type of question, there was a homework question that talks about that. About says access strings. That's all it's requesting is this type of access pattern where we don't focus so much on the precise 32-bit addresses, but we can kind of squint at it and see what it's getting at, right? Location 0 followed by location 5 followed by location 10. The question is really just asking you is to take that, connect that to what the binary encoding essentially of those addresses would be, and then figure out where in the cache for different cache structures those access requests would be. We don't talk yet about whether it's a read or a write. We can assume they're all reads to start with, and then we'll have to talk about writes separately. But for that series of load word operations that we would have here, you should now be able to kind of trace through and say, okay, based on this address, what entry in the cache am I first interested in? And do I have the necessary information to determine whether or not it's a hit or not? This is one way of viewing the cache, kind of the logical layout of what's happening in the cache. I also personally, I would prefer sort of more the architectural layout of the cache, which it's trying to represent the same exact information. It's just more of a layout in terms of if you were to go about designing some VHDL for this, how would you start with in terms of the structure for it? This is showing for now. This is for a 32-bit address field, but for the 4 entry cache and the 8 entry cache, the same exact principles apply here. There's going to be some sort of cache controller. Don't think of this as an entirely nebulous thing. It's going to be some sort of either state machine or just some combinational logic that's a control logic that's helping us determine, takes an address as an input and produces a value as an output. And it has some work to do because it has to first determine whether or not the value that you need is in the cache or if that data has to be found somewhere else at later levels of the memory hierarchy. That's what the cache controller is doing. In terms of that first part of the challenge, which is there the value that's being requested? Is it in the cache or not? Your logic model for that, I think, should ultimately still just be a large memory. Whether it's SRAM or not, we talked about some of the implementation details. It's just a large two-dimensional layout of bits, of which each so-called row in the cache or each entry in the cache corresponds to a particular index. So in this case, if we're told that there's 1024 indices in the cache, that many quote unquote rows in the cache or blocks in the cache is also we could use correctly here in this context. If there's that many, then we're going to take 10 bits of the index from our address and use it effectively as the lookup value for this custom memory. And again, what separates a hardware cache from a sort of software managed cache, which we do all the time when we write software, is that there's hardware mechanisms that allow us to determine whether the value we want is in the cache or not. The load word instruction doesn't need to be aware of whether or not the value is in the cache or not, based on not just the data that we're storing in this memory, but the what we were calling the metadata, right? The additional information that also has to be stored, that overhead of bits we have to store in the cache, allows us to relatively efficiently determine at load time, yes, the value you requested is in the cache or it's not. So it's a lookup into this row of our memory, this location in our memory, and we're grabbing the data we potentially want, the actual word we wanted of our data for our load word operation. We're also simultaneously, this could be definitely a concurrent or a parallel operation here. We're grabbing those tag bits, and we're also grabbing that individual valid bit that we talked about. And so consequently, our cache lookup operation involves assuming the values there we want to start with, but then also just taking a look at that tag and checking if the value we loaded from the cache is actually the same as what's encoded in our address, the remainder of those tag bits. And we have to use the remainder of the address as our tag bits. We can't just say, well, this is a 32-bit address, but that's a pretty large tag. And that would be, right? Much more of our storage here would be tag bits than would be actual data bits if this was a 1 byte block that we were talking about before. That's very inefficient in terms of how much extra stuff we have to store in order to store the actual data that we're interested in. But we do need to put the entirety of the remainder of that address in as the tag. We can't do half of it, right? Because if we do half of it, you may look at it and say, well, 11 bits is enough. Why do we need all of those 22 bits to store as the tag? This is kind of like a hash function as I talked about on Monday, but it has to be a minimal perfect hash. It has to give us a guaranteed result. Yes, this is the value that you've stored in here, or no, this is not the value that you have stored in here at that address. And so we need the entirety of the address to basically disambiguate and say, yes, this is the address you requested, or no, this is not the address you requested. So it seems inefficient because it is inefficient. It's a hardware overhead. It's spending more hardware real estate on tag storage than you would otherwise need if this was a software managed cache. But the benefit is now the software doesn't need to look at this at all. Software just provides an address. That same address calculation logic you implemented for Project Part B doesn't change. It's exactly the same. It's now connecting not to just a very simple little memory that we're implementing for our FPGA based synthesis. It's interfacing to a controller that's doing this lookup and then also doing that comparison logic for you and determining yes, tag equals and valid is high, then that is a hit. If either of those things are false, either it's not valid to begin with, or if the tag is not a match, that is our miss in the cache. So again, those delays that we've been assuming, and we'll get to the quiz in just a moment here. People are still trickling in, so let's get to the quiz in just a couple minutes here. Those delays that we've been assuming that everything fits in that single cycle of our pipeline. That's really been assuming cache hits, and we talked about that a little bit last week, but I just wanted to reiterate that here today. For that pipeline to work, we have to assume we can access the vast majority of our data that we're interested in, directly in the cache. And that's our assumption. And that turns out to be the case in practice, that is the case. And I mentioned 95 to 99% hit rates for caches because of temporal locality and because of, and we'll talk about how that would work in terms of spatial locality as well. There's enough of that in commonly used programs that you can have this relatively small cache, and the stuff that your program tends to need will be found in there the vast majority of the time. Because if it's not, if there is that cache miss, now life is pain. Now we have to wait for a significant amount of time to go access at that next level of memory. Could be next level of cache. It could be your main memory. It could be all the way on your hard drive. Potentially, that's sort of the worst case scenario, or it could be off on the network somewhere. The simplest thing to do would then be, if that happens, if our load word instruction happens, we would just stall and say, okay, the values that we want are not in the cache. Pipeline, you just have to wait. You have to wait for 100 cycles or 200 cycles. That's the assumption we'll work with for the remainder of this semester. Modern microarchitectures put a lot of extra thought and design into how to hide that latency even more. GPUs in 480, which you'll learn more about, cover or really invented effectively to do that. recognizing that there's going to be a lot of misses in the cache for that particular workload as compared to a general purpose CPU workload, just have enough threads that are potentially active so that even if this one thread has to stall for 100 or 200 cycles, it's okay because there's always another thread we can put on very quickly. And as long as we always have enough threads to put on that are ready, we can just kind of hide that latency. But for our 5 stage scalar pipeline, there's really no way we have to hide that latency. If we miss in the cache, we have a pretty long delay ahead of us. And it doesn't exactly show it in this figure, but it's really just the reverse operation. So if we have a value that we now need to load into the cache because we had the miss, so we want to grab the value from main memory or the next level. We want to return that value in our load word, but we also simultaneously want to return the value into the cache as well, right? That's the whole purpose. We've missed in the cache. Our hope is we don't have to miss in that same address again. Let's not only just return the value back to the CPU, let us also provide the value into the cache as well for the next time. And this diagram doesn't exactly show entirely what's happening, but it's really just that. It's the converse operation. It's we have the data that we're going to return to the data path for our load word operation. Let us also update that value in the cache. Maybe that's obvious that we're doing that as well. We're also not just updating the data field, but then we're also having to update the tag field and potentially the valid field for that particular location. So it's the same exact operation, just now our reads are also kind of doing a write, if that makes sense, right? We're reading from that next level of storage, loading that into the processor, and simultaneously we're also writing to this memory. So as you start to deal with multi-level memory hierarchies, reads versus writes, you have to be pretty precise with your language. I mean, I think conceptually it's relatively straightforward, but who is reading, who is writing, who is loading, who is storing? In this case, from the CPU's perspective, this is a load operation. From the cache's perspective, if there was a miss, it's also a store operation because I'm updating the cache in the process of also updating the CPU with that particular value. And when it's a cache hit, then it's a little bit more directly connected to the terminology we've been using. We're loading from the cache and then we're loading into the CPU. And we're not having to necessarily update the cache very much. So we have to be a little careful about what it means to have stale values in our cache here. If we're just doing reads, though, if we're just doing reads, we're never going to have stale values in our cache. Sometimes there's a little bit of program intervention required for that. If we know that our backing store is not memory, but it's actually some I/O, then we probably don't want to cache it at all because that's potentially wrong data that we would have in our cache. But if we're just reading from main memory here, the values in our cache are always going to be for single core processors. Someone mentioned that on Monday already. For this case where there's not this shared memory model that we're working with, single thread, single process, single processor accessing memory. In that case, the values that we have in our cache for read operations are going to be old in a sense that they've been there for a while, but they're not going to be wrong. So they're still valid. They're still representing the correct result that would have been fetched if we were to fetch instead from our main memory. So that valid tag isn't actually for that. We'll have other ways of using that if we have to then invalidate some value in our cache. But if we're just doing loads and it's single processor, there's a lot of caveats for this still to be the case, and no one else is updating that main memory separately from our process that is doing it, then the value, if there's a valid bit, is going to correspond to something that's valid in memory. We don't have to worry about that in this particular instance here. Um, and so we had those multiple questions, and that final question is what do we do when our cache fills up, or if we have to reuse a block for a different memory address? For the direct map cache, and this is the downside of the direct map cache. This is why you see them in use, but they're considered the most basic of cache architectures. We have effectively a type of policy, and it'd be referred to as a least recently used replacement policy, which is just anytime something new is ready to come into that location in the cache, we would automatically just overwrite what was previously stored there. And that is why that access string of 0, then 4, then 0, then 4 would correspond to misses all the way through. Because we'd be updating the value of that same exact block in the cache, and we'd be effectively implementing a least recently used policy. It's kind of by default with the direct map cache. You only have one place every address could potentially go in the cache, and consequently, only what's most recently fit in that cache is what's going to be stored in that cache. that is a downside of the direct map cache. And when I say next lecture, I mean in about 5 minutes here, looking at how we can have better policies for replacing things in the cache. Let's pause here for a moment. Everyone, collect yourself, and let's take a look at Canvas. Canvas is pretty much done for the semester in terms of our schedule at least. There was an email that came this morning that said that everyone had added one new statement to their syllabus. So I did add that statement, but it doesn't affect anything for this class. We're behind on our quizzes, so there will not be a quiz 12 at this point. And so we are technically today on quiz number 10. So go take a look at quiz number 10 and not 11, because that one, it may say it's open, but the quiz I would like you to do today is quiz number 10. I'll put that in the chat for people who are only kind of watching and not listening, which some people do. Um, and the code is listed as there, and I'll type it into the chat as well if you just want to copy paste it. So let's take. I think we can get this done in about 2 minutes here, but take the time that you need, and you know, kind of those of you who are done, just kind of make eye contact again with me, and then I know that you're done with the quiz, without giving away too much private information here. And yep, I got the code on there. So get started on this first quiz question, and let's take about 2 to 3 minutes.